Good morning. Am I audible?
Yes, sir. Good morning, sir.
Yes, sir. Good morning.
So let us start. Is the presentation visible?
Yes,
Yes,
sir.
sir.
So we have been talking about testing strategies, and we have discussed black box testing strategies, different things like boundary value, like equivalence classes, and so on. Black box testing, as we observed, is primarily useful for testing against the specification. Right? So it is a primary validation method and can be, for example, the user acceptance test is necessarily a black box testing. But for the details of different tests and bugs in the program, we need to take recourse to white box testing, where the entire internal of the system, that is the entire code, the headers, the source files, all are available. So in white box testing, primarily there are two approaches. One is called the coverage-based testing. That is what you want to ensure through coverage-based testing is different program elements, whether they are individual source lines or they are functions, or there are certain branches in the program, or certain paths that the program can take from the beginning till the end. We want to test whether the given test cases have executed those program elements. So if a test case will execute a particular line or a particular function, that does not and the end result is correct, then you have some confidence on the correctness of that line or the function of the branch. Of course, there may still be bugs because it's a combination of several things. But certainly, if a line has never been executed while running all test cases over the program, that is the entire test suite, then certainly there is a surprise waiting for us. Or if a function has never been called, then the question is whether at all that function is needed, or under what condition that function gets called, and when it gets called, will it work really properly. So the coverage-based testing is a very strong method and widely used industry method for testing the different programs before shipment. The other approach is to do fault-based testing. That is, fault-based testing particularly is important for testing the exception paths. For example, if you put all correct test cases, then naturally the different failure conditions or exceptions will not arise. And in some cases, it may become really difficult to design a test case which will cause a particular fault. For example, your exception is on low memory. Right? You are doing a memory allocation in the program, dynamic memory allocation, and the new fails because there is not sufficient memory available. Now, it is extremely difficult to simulate that situation in many cases because you will really have to run out of memory in the system, and then kind of it causes a additional difficulty because you are testing the system, testing the software on your system, and if the system runs out of memory, then your tester itself will stop working, because there is not enough memory. So what you do is you inject a fault, kind of intentionally. That is, you mutate the program point, and when the allocation is happening, you just falsely put that detection that the memory has been run out, right? So actual new has given you a valid pointer, but you just suppress that and set that pointer to 0, or forcefully through an exception at that point that you have low memory. So what you're doing is you are simulating a fault by mutating the program, and then see whether the exception path gets properly covered. So mutation testing, which is a fault-based testing strategy, is very useful for such kind of exception paths. So these are the two primary avenues. So we have limited time, so let me just give you a quick glimpse of some of these approaches. I have already explained this. So the line coverage basically tells you, there are standard tools, and I would encourage you to try out those tools like GCOV, LCOV, which are free GNU tools. So you can just download and use them. You can use them online also. So that if you run your program through this particular tool, it will at the end tell you what are the lines in your program that has been executed and how many times they have been executed. So some line may have been executed 5 times, some line may have been executed 20 times, some lines may not have been executed. Right? So to prepare your program in a way that is amenable to such kind of testing, you should make sure that like 2 statements are not written in the same line, because they'll be counted only as one. Or particularly for a if condition check, suppose you have if x greater than y, max is assigned x, otherwise max is assigned y. Right. Now, of course, this is not correct, but suppose this is what is written. Now, what will happen if x is greater than y? If you are in this line, if x is not greater than y, then it will not execute max assigned x. Right? But your coverage tool will tell you that this line has been covered because you have done the test x greater than y. So you should write it as into separate lines. If x greater than y, in the next line max assigned x, and then the rest. Right. So this is the basic line coverage. So line coverage is typically given in 2 forms. So one is called statement coverage, or the line coverage. The pure line coverage is textual, which tells you the total number of lines, the number of lines executed. Executed means executed at least once. Some may have been executed multiple times, but you count the lines which are executed at least once, divided by the total number of lines, and you multiply it by 100 to get the percentage. Right? Statement coverage is similar. So this line coverage, now it is extremely difficult for any reasonable program to achieve 100% line coverage. So your organization will have a certain, release criterion to say that, okay, a software can be shipped if the line coverage is more than, say, 80%, or it is more than 70%, or it's more than 90%, but 100% is certainly not achievable. For example, if you see this following Euclid's algorithm for finding GCD, the question is, how can you get the complete line coverage? Now, the first line will obviously get executed. The second line will get executed on any test case. The third line will also get executed on any test case. But the fourth and fifth lines may or may not get executed. So if you want to force, say if you give 4 3 as an input, 4 and 3 as an input is not equal, 4 is greater than 3, so this fourth line is executed, right? And then x becomes 4 minus 3 1, right? And y remains 3, so you have 1 3 1 3, you come here, so the other fifth line is also executed, right? So simply just having a 4 3 will attain a 100% line coverage in this case. But considering the notion of the black box testing and different equivalence classes and boundary conditions, we will probably have this kind of a test set. Or given that it's a GCD algorithm, we'll probably have some more specific test cases, like when one of the numbers is divides the other number, or when the GCD is actually 1, and so on. Right? But this is the basic requirement for a statement or line coverage. In contrast, function coverage is about how many times a particular function has been called. So the coverage tool will tell you that how many times a function has been called, and the function coverage is the number of functions called at least once divided by the total number of functions. So it's typical mandate of most organizations is that you have a function coverage which is 100%. Right? Every function must have been called, otherwise there is no reason that the function should be there. And you may note that the function coverage is different from the call coverage. Function coverage is a function has been called, but a function may have a call site at 3 places. Now, if any one of the calls happen, then the function has been covered because it has been called. But that does not say that all possible calls of the function from different points have happened. And so that is known as a call coverage, where you check whether each and every call of the function has been executed. So that is called the call coverage. Right? Naturally, call coverage is somewhat more difficult to attain, but having a 100% call coverage. Now, if you have 100% call coverage, then you have a better confidence. But certainly, you may have 100% function coverage, but not 100% call coverage, which is common. And interestingly, you may have a 100% call coverage and may not have 100% function coverage, because there may be functions which have not been called at all. Right? So those functions should be removed. So these are the two basic coverage metrics which are used by tools like LCOV, GCOV. Now, what you try to do further is check, since there will be several condition checks. So you would like to check if every branch of a particular program or a particular function has been covered or not. For example, if you see in this given code, if I have a test case which is x equal to 0, then it will cover all the lines. While x is equal to 1 covers only 1 to 4. So with x is equal to 0, we will get 100% statement coverage. But that does not, so the statement coverage will be fine, but that does not check the jump that exists, which is invisible in the source code. It will be there in the assembly. That does not tell you that there is a jump from 2 to 4. And that jump has not been tested. Right? X is equal to 1 actually tests that jump. So, so that is very important. And branch coverage usually will give you a better coverage than your line or statement coverage. And there are certainly certain tricky codes, like if I have if true, then you can never get 100% branch coverage, because to jump 1 to 3 will never execute. So you'll then need to take recourse to mutation testing. That is, you have to inject a fault here to make this true as false, and then force and see what is happening in this case. Okay, so now for the branch coverage, you typically make a control flow graph, right? And so that you can see the all possible branches. For example, if I consider this GCD program, what are the branches? From 1, there's a condition check. So from 1, the control may go to 2, or it may directly go to 6 if they're already equal. Right? So you have a branch 1, 2, a branch 1, 6. There's a condition check at 2. So it can go directly to 3 if the condition is true, and it can go to 4 if the condition is false. You have 2, 3, 2, 4. After doing now these are the explicit what you can see. Now that's the reason you need to have a control flow graph for the program. I'll just show you a sample of the control flow graph soon. Now what you cannot see is after doing 3, you have to jump to the end of the loop. Right? So after doing 3, you will jump here. So there is an invisible jump here. It will jump over the else. So there is a branch from 3 to 5. Then after doing 4, you will come to 5. You do not know whether the code actually does a fall through or the code has a jump there. So you assume that there is a branch. Another invisible is the backward jump from 5 to 1 when you are at the end of the loop. So the 5, 1. So you can see that in this small program itself, there are 7 branches. And if you have to test for them, for example, if you take x and y equal, then you certainly check for 1, 6. If you have 4 and 3, that is x is greater, then you check for 1, 2, 2, 3, 3, 5, 5, 1, similarly. Yeah? So you find out what are the total number of branches in the control flow graph, and the executed branches the tool will count, and then you express this in the percentage, and you have a branch coverage number decided. Right? Now it is if you have covered all the branches, then it will satisfy that you have the statement adequacy, but not the other way around. We have already seen that you may have covered all the statements, but not all the branches. Condition coverage is a refinement on the branch, or rather, it's add-on to the branch coverage, which says if I have a condition, did I check every part of the condition? As you know that conditions also internally give rise to branches, because there is a shortcut. For example, if you are doing digit high is equal to 1 or digit low is equal to -1, then if digit is high, this is true, then the second part is not executed at all. So this second part of the condition is not executed at all, because it takes recourse to the shortcut execution. Right? So you have to make sure that all conditions are also covered, and that gives you a naturally better confidence. For example, you have a statement condition like this: C1 and C2 or C3. Okay? Now, each of this has to be exercised at least once. Right? They have to be given true and false values, and thereby you can have a good condition coverage. Let us skip some of the following and let me move to path coverage. Path coverage is a built-up of that, where you construct the control flow graph and find out what are the possible paths. It's a graph, right? So in the graph, you know how to trace a path from the start node to the end node, right? That's the beginning of the function to the end of the function, let's say. So path coverage on the control flow graph, you'll have to see that all paths have been covered. Let's see an example. Again, the GCD program. So it says that this is the control flow graph. As I said, that is the example. Control flow graph 1, control goes to 2 or to 6. From 2 it goes to 3 or 4, and both from 3 and 4 it comes to 5. From 5 it goes back to 1. So what are the paths? Now 1 certainly is the beginning, is the entry node, and 6 is the exit node. So you have a path which is 1, 6. You have a path which is 1, 2, 3, 5, 1, 6. You have a path 1, 2, 4, 5, 1, 6. Right? So these are obviously the paths. Now, the point is that since there is a loop here, so I can have a path 1, 2, 3, 5, 1, 2, 4, 5, 1, 2, 4, 5, back to 1, 6. That also is a path. Right? So what you define is that the notion of a linearly independent path, which says that a path through the program that introduces at least one new edge that is not included in any other independent path is a linearly independent path. Otherwise, it is not a linearly independent path, and you need not consider that. So when you go over the loop, you will easily realize that going through the loop will not make them linearly independent paths. So you have just 3 linearly independent paths that exist. Just another example. And it puts n to 2. Then while I is less than I to 2, while I is less than n, it checks if I divides n. And if it does, it returns false. Otherwise, it's a brute force prime checker. Right? So it's doing that in the brute force. So if I look in terms of these statement numbers, which we loosely mark here as nodes of the control flow graph, ignoring the closing parenthesis, which actually does not have a computation, then this is how it will look. You have A, from A you go to B. From B you can go to C, or you can go to F. And from C you can go to E or D. You can go to C, you can go to D, or you can go to E. From D you can go to exit. Right? So this is, given this control flow graph, you have actually 3 linearly independent paths shown in 3 colors. Right? So there is a linearly independent path analyzer which does that. And based on that, you find the path coverage. Now, there is a nice metric which is commonly used in terms of checking, how complex your program is, or the function is, and that is related to the maximum number of linearly independent paths. So this, if you consider this as a graph, and compute this number E minus n plus 2. E is the number of ages, right? So you have here 1, 2, 3, 4, 5, 6, 7. 7 ages. And n is the number of nodes, which is 6 here, plus 2. So that will tell you what is the maximum number of linearly independent paths. This is a graph theoretic result, so we are not going into the explanations of that. And it also has a correlation with the number of bounded regions. For example, 2, 4, 5, 3. This is a bounded region. Similarly, 1, 2, 3, 5. This is another bounded region. So this number equals the number of bounded areas plus 1. Right? So that is another. But this number is important because that tells you what is the maximum number of linearly independent paths that are possible. And it is known as the cyclomatic complexity of a function. Okay. Certainly, many companies mandate that a certain number for the cyclomatic metric for a function, right? So that a function does not become very complex. If it becomes very complex, it is very difficult to test. So that should be broken down into smaller functions, so with lesser cyclomatic complexity. Right? So this, and it was introduced by Maccabe, so it's often called Maccabe's metric. So let us, so this is, you can now see that the path coverage is simply draw the control flow graph, determine the cyclomatic complexity, and then you know how many maximum linearly independent paths to find. You find the linearly independent paths and prepare the test cases so that you can force your execution through that. So this is the basic approaches. Let me, so in terms of a overall strategy structure, we can see that the simplest is a statement coverage, which has specializations in terms of condition coverage and branch coverage. And there are several refinements of that. And branch coverage as independent path analysis, as we have just described, and then you have path coverage. So as you come down in this hierarchy, you have more and more complex coverage testing, and which gives you a better and better confidence on the test result. So this was just a glimpse of the white box testing. Let me jump. There are a lot of details given here also about tools which you can. I'll just obviously share this and refer to that. But let me jump to test plans that you need to do. We have been talking about test plans. Okay? So I have 3 quick examples to show. For example, if you consider the leave management system, then your test plan could be this kind of tables which tell you which operation has to be tested for what kind of leave. For example, if you're considering the quota of the leave and there's a credit being made, so obviously duty leave had no credit, but every other type of leave will have credit. Carry forward is the same. Encashment will be there only for the earned leave. So this is kind of a plan that you give to the test designer, so that the test designer now have to fill up all these open boxes. Okay? That it has to create a test for credit of casual leave, credit of earned leave, so on and so forth. Similar thing you do for the leave period. The financial consequences of a leave, whether it is encashment or whether it is credit, whether it is salary reduction, that is debit for a leave without pay. Then for leave conditions and so on. So what we are trying to do is to create a document saying that what are the different test cases that will go in your test suite, right? So that could be a starting point. So that is one kind of example. Let me show you another example of a function which solves a quadratic equation. We discussed about the QES as black box testing. We have seen the different equivalence classes, and now we are going to look at that to the classes of white box testing. So now you have white box. You have all the entire code. Okay? Now what you do, you form the CFG control flow graph of that code. It is it's not easy to see it here, but you'll have to put it on big paper and work out. These are the line numbers given. So for example, you start at 1, you'll come to 2, then you'll come to 3. Till that is fine. But from 3, you could go to 4, or you could go to 14. So 0, 1, 2, 3. From 3, you could go to 4, or you can go to 14. Similarly, from 14, if you have come here, then from 14 you will go to 15 and then proceed. So you form the control flow graph, and then certain parts of the control flow graph you can reduce. For example, there are long paths like 4 to there are nodes like 14, like 10, 14 here, or 10 here, which are actually do not have any computation. They're just there for the syntax of the language. So you can remove those nodes, and as you do that, you'll find that you have a much reduced control flow graph. So on this control flow graph, now you can find the different. So this is the code. These are the equivalence classes. And on this control flow graph, you can find the different statements to be tested. Obviously, there's no function testing because you are doing only a single function. Then you can see what are the different branches. At every point, you can see the branches, right, wherever the branching is taking place. So you know what are the branches to test, and you can find out what are the paths to test. Right, this is the path. 2, 3, 15, 16, 17, 18, 31. This is a path. So here is the code again. These are the equivalence classes based on the knowledge of the black box. And these are the final tests and coverages that you can get. For example, if you use the infinite root, then you see what are the statements that you get covered. 0, 0, 0. So A is 0, so you are at, so you have done 2. A is 0, so you do 3. Since A is 0, you do 4. Since B is 0, you do 5. And since C is 0, you do 6. And after that, you jump. Basically, it's all these ifs will have to get jumped, and you come to return value. Let's A is 0. Here in the control flow graph, it is easier. 2, 3. Then B is 0. C is 0. Then the return value, and finally the end. So these are the statements which get covered. You can also put down what are the branches that are covered and what are the paths that are covered. And if you have analyzed the the linearly independent paths, you'll be able to see whether with this you have covered all linearly independent paths, whether you have covered all branches and so on. So your test plan will have this analysis, and final output of the test plan is this test suite. Of course, here the goldens are not given. Goldens will also have to be given in the test suite as to what outcome you expect. So then finally your tester looks something like this. Is a main driver, the tester driver, which invokes solve and gets the return value. Okay? The return value, basically, if you see, the return value is telling you what are the different cases. In which case does it fall? Whether it's infinite solution case, inconsistent equation case, linear equation case, and so on. And A, B, C are input parameters, and naturally R1, R2 are reference parameter for your two roots. So from this return value, you know which case is getting tested, and you can print. Here I'm just printing for human understanding. But what you can do that then, if you are in case 2, you have repeated roots, so you have to check whether these roots are equal to what the golden has given. Right? So this is basically what goes as a part of a, like if you have an algorithmic stuff, then this is how it, the plan for it can be prepared. Let me show you a different kind of a test plan, because test plan is not something which is, I think at some point some of you were asking that could I have a structure of a test plan or kind of format of a test plan. It's very difficult to have a specified format for the test plan because it does vary depending on what you want to test. What are the functionalities there? So let us try to look at a test plan for a red-black binary search tree. Are you familiar with red-black tree?
No, sir.
You have, I mean, you have done, say, binary search tree,
Yes, sir. BST is.
BST, So AVL tree,
Yes, sir, but not red-black.
Red-black. So the basic idea of, the binary search tree is a binary tree where every node has a left subtree with all values less than that and a right subtree with all values greater than that. And the basic problem of a binary search tree is that it may not be balanced. So if it is not balanced, then it cannot have the right performance in terms of search, insert, and delete. Right? So your basic idea is to balance the binary search tree so that kind of you can get a login number of operations in that. So there are different strategies for achieving that balancing. One is a very hard strategy like in AVL tree, where you say that the difference of height of the two left and right subtrees cannot be more than 1. And the reason it is one of the first balancing strategies that was proposed, but it is hardly used ever anywhere because it has a lot of complex node rotation operations. You have already seen the single rotation and double rotation, which are not only difficult to write, but given that these rotations involve so many pointer manipulations that even though in the complexity analysis it is order of log n, but in the actual runtime it is not a very good option. So there are different other strategies like randomization, amortization and all that. But red-black tree is a very simple tree where you can achieve, you basically mark the nodes as red and black, and you can very easily achieve the balancing. I cannot teach you the red-black tree right here, but it's a beautiful data structure, and it's kind of the foundation of the generalization of red-black tree is actually B tree, which is used in databases. So you must learn that. So I mean, you'll be able to understand the test plan even without that. So what we want to do is we want to, we are implementing such a red-black tree container. And it's a container because it contains number of data nodes, and it can do operations like insert, delete, search. Of course, it could do a lot more operations like usual red-black trees can do union. If you have two red-black trees, you can do union of that. You can do splicing, all of that. But so we need to set up a regression for this so that if some bugs are reported and in future we have to fix a bug, then we can do a regression test. Right? So what are the components that will be required? The test plan will tell that I need a regression application. That what will, a driver which will take the test cases, run it through the red-black tree container and generate the report and so on. Then we need the regression tests itself. And what will a regression test have? It will have a sequence of data, right? Because there could be insert, delete. So it's just not only one single, but it could be sequences of insert, delete, search, this kind of. So sequences of data. And naturally, with that, the instruction or the command that I want to do. So I say the data is 3, 5. The key is 3, the info is 5. The data is 3, 5, and the instruction is you insert. Right. And then you have to create golden for different cases. For example, what are the basic operations? One is create the tree, find pass, key info. That is, find pass means that you will provide a key which you know exists in the container. Right. So you are doing a find operation, and the type of the test case is a pass. That is, you are expecting it to pass. Then you will have find fail. That is, you are giving a key which you know at that point should not be there in the container, and you expect a failure. Similarly, you have insert pass. That is, you are being able to insert a particular key. You have insert fail. That is, you are trying to insert a duplicate. You can check for the validity of the tree, which is of course internal as to whether it satisfies the red-black conditions and so on. Finally, release the tree, not considering the delete for now. So this is broadly what it will. So it will also need a particular folder structure. Let's skip that details. So the first that we'll have are functional tests. That is, you're checking for the functionalities. So we have create and destroy tests should be there. This will test various constructors and destructors. Okay. For example, default a tree, tree with a single node, or copying a tree and so on. Then we should also test for if the tree is instantiated as an automatic data or if it is dynamically. So that's the create destroy functionality. Then you will have insertion tests. This is a normal test case without duplicate. Test arising from arbitrary sequence of 5 insertions, 10 insertions, 15 insertions like that. So here you are not writing the test. So this is a plan. So this is, whoever is writing this is thinking of what is kind of required and sufficient for testing that part of the functionality. Duplicate insertion, similarly, find tests for existing keys, for missing keys. deletion test, existing unique keys, existing duplicate keys. If you have duplicate insertion is a fail, then you will not have this. Missing keys and so on. Then you'll have further functional tests like can you print this tree? Can you traverse the tree? Can you traverse the tree in a sorted order? Can you write visitors on this tree? Visitor you still do not know, I suppose. After the functional test, now you will have to also plan for API test, right? Because certainly whoever will use this will use it through some function calls, APIs, right? It's not going to directly use your class member functions or things like that. So you have APIs. These APIs could be just C functions or public member functions or basically interface functions, whatever way you have designed. So you need to check for those functions. The third set, which is very typical for a test plan, is the group of tests which are directed corner cases or tests from implementation. A directed test means that so far you have been just looking more, you are doing a white box testing primarily. Actually not, because if you look at the functional tests here, then if you categorize this in terms of strategy, this basically is a black box testing that you have done, right? Because we are checking the functionalities. APIs are also kind of black box testing, but now you want to look into some of the specific white box cases. That looking at the implementation, the direct test is a certain focused specific test which you want to do, which may not be related to a particular value. But for example, you want to check for empty tree. It should be possible to construct an empty tree at present. What happens if you have a tree of a single node? Then from the implementation, you know that there are different rotations. Red-black tree has a concept of shifting the red and black colors. So color shifts, splitting of roots, so on. The basic steps required in the red-black tree algorithm, you would like to test that. Right? So these are the different types of directed tests. Empty tree with a single node is a corner case. But overall, these are all tests that you are designing from your knowledge of the implementation. With that, you have multiple trees within the same scope, that is within the same lexical scope. Can you have multiple trees instantiated? This will expose if you have, for example, use some static values, then you will get into a problem with multiple instantiation in the scope. Those which have disjoint lifetime, those which have overlapped lifetime, like two trees which are in the same scope, but one does the operations and is wrapped up, destroyed, and then the second is instantiated, is one scenario. The other scenario is there is a point where both the trees exist, overlapped lifetime. Then you have a set of negative tests, that is things that should not be possible, like no copy test. The tree, it should not be possible to copy the tree. No assignment test. The tree should not be possible to be assigned. Right? Most of the STL containers, if you see that they are not, you cannot copy or move them, many of them, or copy or copy construct or copy assign them. You can only move construct or move assign them. Some can be copied also, of course. It depends on what is your original specification. But if no copy was specified, then you have these tests which are different directed tests. Then a Another is kind of a what is you can call a big test. That is where you just do certain kind of, for example, a tree from a long sequence of monotonic sequence. You know, if you think about the AVL tree, if you give a monotonic sequence, that is, sequence of increasing numbers or decreasing numbers, then at every point the tree tends to get skewed, and you have to take care of that. So monotonic sequence is a particular corner case for these kind of containers, balanced containers. Then trees arising from long alternating sequence of insertions, right? Increasing, decreasing, increasing, decreasing. I mean, you just think about different scenarios. So this was the third set. Then the fourth is what is the use model and extension test? Right? Can you add a name to a tree? Can you change the type of the key in the data node? Right? Can you change the type of the info in the data node? So this will be possible if you have done this container with templates. Can you allow for multiple keys? If multiple keys by accommodating a resolution on secondary key, right? Multiple keys with the same key value. Right? Then you have a group of random tests, right? Where after all this logical thinking and so on, you could just have a random number generator to generate the keys, and you do a huge random number of tests. You could specifically do low memory test. Okay? Then you check for the quality parameters, like it should have zero memory leak, it should have zero memory access error, performances like peak memory, memory key info pair, time to insert, time to find. These all. Now, it obviously depends on your organization's objectives and commitments, the SLA, service level agreement, that you have for the software with your customer. But this is what typically a test plan would look like, which truly a plan. It's not, based on this now, for each and every case, adequate number of test cases will have to be created. Then for those, the goldens will have to be generated. So initially, at the initial phase, you may have a very kind of painful manual intervention to create or check the golden. Or alternatively, what you can do is, if you have some other container already tested, which has the similar operations and properties, then you can get the golden generated from that container and use it here and check whether it's. So that's very, at a very top level, what testing is kind of the glimpses of testing. But there are several slides which I could not discuss because lack of time. Please, not for the examination, but for your actual, information, because testing is something very deep that you should know very well. For that, you should go through this and the links given therein, and you will have a much better grasp of the overall software engineering paradigm. Let me see if you have any questions here. Friends, any questions? So I think the semester was shortened and we couldn't do justice to much of the software engineering aspects. We just had glimpses of SDLC, some bit of UML and testing. There are several topics, even in testing or in UML, that we could not cover, but at least it will give you some idea. But I think good coverage we have done in terms of the actual training in the C++ as a language. And mind you, what we have covered is about you know about 25 years old, dated by 25 years, because we followed the C++ 98 standard, and at present the standard is the C++ 20. And learning those, which you should be able to self-learn very easily based on what you have already seen, is extremely required, because it not only it gives you a lot of insight into the programming systems, but it will also give you show you the way how you can write the same functionality with a shorter amount of code and make it easy to do, or make it correct with a much less effort, because the standard library has been substantially enhanced. There are a lot of features like move constructor, R value reference, move assignment, lambdas, all that have come in, which makes it really, really rich. So I would suggest that please go through that. There are in NPTEL, there is a course called Programming in Modern C++, which I take. So those videos are freely available. So, and the presentations also, you could refer to them to strengthen your knowledge about programming in C++. Okay, any question in general or otherwise, because this is the last interaction that we are having. The next will be your scheduled test on next Friday.
Sir, may we know the syllabus of the test, sir?
Syllabus of the test, whatever has been covered?
Okay, means the whole syllabus, sir?
Yes, yes, of course.
Okay, sir.
I mean, how can you have a part of C++ or a part of software engineering? So the whole thing will be there, and the presentations that I have used in the last couple of days, I will send you across. So both on.
So can you provide us?
Provide you what?
Sir, the course outline, so that we could see what things we have missed due to the semester being cut short.
What we should have done.
Yes, sir. Although everything which was cut off.
Yeah, that was. I mean, at least 25% was cut off. That's very unfortunate. But did I share you the syllabus document, the modified syllabus document? I mean, that is a document of what we intend to do. Of course, that is little more than what can be done in a semester, but I will share you with that document, because that will keep you the perspective of what you should keep on learning. You know, because in today's time, you learn probably a lot more beyond the regular scheduled classes through your peers or through the net programs and so on. So you should keep focus that these are the things you must master. I'll share that document. There is a 2-page document which says what is the intended outline of this. And you will see that of that, since the semester was short, that me and Professor Shorangshu decided that C++ programming we should not compromise with, because at least that's a concrete skill all of you must have. So you need it at every point. And but on the different software engineering strategies, so different things, a lot of things have been compromised. Right, I'll share that. Any other question? Professor
Sir, I have a
Shorangshu?
comment.
Yes, please.
Sir, it's just my 2 cents, but I think that C++ course, it would have been great if we had several other things which are used in real life into software engineering, and C++ should have been a separate course, like
Yeah.
intermediate programming. Or
we cannot agree more, but unfortunately, given the credits and the core course and all that, we could not accommodate for several years, we could not accommodate a course on object-oriented programming. There should be a course on object-oriented analysis, design, and programming, which should teach this. I mean, you are absolutely right. Now, we bring in C++ heavily here because one is that your core software engineering skill as an engineer involves knowing that software, how to build a software. And you need to know a tool like C++ to do that. You need to understand object-oriented analysis, design, and programming to be able to do that. So I fully agree that it should have been two courses, one that goes in there and the other. Like in NPTEL, actually, it is two courses. NPTEL has a separate course on object-oriented analysis design and a separate course on programming in C++. So at least these two together should have been a separate course, and software engineering should have been different. But that's all that your packed curriculum, BTech curriculum, has time for. So because we are fully aware, and this has been every time the syllabus program is revised, this discussion come up, but we fail to find slots because the main problem is if we are to do that, then it has to be a core course. We can always offer an elective, but then some people will take it, some will not take it. Then you cannot assume that everybody knows this, but we need everybody to know the C++ or OOP skills as well. So that's the difficulty. We do not have core slots left. Okay.
Yes, sir.
Any other comment, question, anything? Hopefully, we'll make next semester possibly in compiler course. You have compiler course next semester, right? Compiler.
Sir, we actually do not know the curriculum of the new curriculum because the ERP hasn't updated the next semester syllabus yet.
Oh, but
we only know the old syllabus.
You mean the old set of course structure?
Yes, sir. Old structure is given, but new is not given completely.
Okay. But I think you have compiler. Then we take it. Anyway, Professor Shorangshu, anything you want to comment on or advise the students?
Yeah, so I think you have covered like all the suggestions. So it was, I mean, as many of the students might know, this was my first time teaching this course. So I also learned a lot with the students and everybody. And I think it was very nice to, I mean, it would have been much nicer if we could have covered the entire syllabus. And I think there are lots of factors. Actually, there was also always the uncertainty that, whether we are taking classes in online mode or offline mode. That also led to a little bit of I mean, we could not finish the entire syllabus. But yeah, so I think it is absolutely essential that I mean, the students should. So one thing is they should practice the C++ programming, but also the related tools. So actually, there are a lot of things which we could not cover in terms of not just testing, but also debugging. So like something like Valgrind or this kind of things. Yeah. So,
sir, those are covered in SPL. System Programming Lab, GDP, and Valgrind is covered for C.
Oh, okay, that's great. Okay.
And we also have done GProf for performance.
Another course covered those topics.
Okay, great. So then that is covered. So just I don't think I have any other concrete suggestion.
Okay, then. Thank you, Professor Shorangshu. All the best, students. Meet you for the scheduled test on next Friday. And regarding the test, planning for that test and the way it will be conducted, we will certainly send you a mail in advance. Thank you very much. And I look forward to meeting you face to face next semester. Thank you. Bye.
Thank you, professors.
Thank you.
Thank you, sir.
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 Thank you, sir.